The size p of a certain insect population at time t in days obeys the function p of t equals 800 e to the 0.04 t. In part A, we want to determine the number of insects at t equals 0 days. At t equals 0 days, we're going to use our function p of t equals 800 e to the 0.04 t. If t is 0 for 0 days, we'll substitute a 0 in for time and get 800 e to the 0.04 times 0. That's 800 e to the 0, because 0.04 times 0 is 0. E to the 0 is 1, and 800 times 1 is 800. So the initial population of insects, or the number of insects at t equals 0 days, is 800. In part B, it says, what is the growth rate for the insect population? And the growth rate, which we usually call K, is going to be 4%. So our K is 0.04, or 4%. That is our growth rate. In the next part, it says use a graphing utility to graph the function. Let's take a look at our calculator. In the y equals menu, I would graph the function 800 e to the 0.04, and I'll use x instead of t. You can take a look at the graph. And the reason why we're not seeing anything is because our initial amount is 800, so we're not really seeing a good picture. So what I like to do is take a look at the table of values, and you can see with my values around -2, my y values are in the 700 range. We know when we get to 0, the y value is going to be 800. So I really need to adjust my y scale. For my y scale, let's adjust it to be starting at, maybe starting at 0. And let's go up to 1,000 for now, but we might adjust it again. So now we can see that curve. And because I'm not seeing the increase on the right here, I'm going to go even higher. Let's go to, let's say 3,000. Okay, so now we're kind of seeing the full picture of the graph. And let's explore what the next part says. Then it says, what is the population after 10 days? Here, population after 10 days. There are a few ways that we can work this out. We can do just like we did here, population at 0 days, where we substitute 10 into the equation. That's 800 e to the 0.04 times 10. We can type that in our calculator. That's 800 e to the 0.04 times 10. Don't need that parenthesis there. And after 10 days, our insect population grows to 1,193. Now another option, if I go to the graph, is to use a feature in the calc menu. So I'm going to hit second, and then trace. That pulls up the calc menu, and number 1 is value. This allows me to type in an x value of 10, and it's going to tell me what the y value is, 1,193. Okay, let's see what the next part says. The next part says, when will the insect population reach 1,200? Okay, so what I'm going to do is substitute 1,200 in for P of t. P of t is the population after time. And then solve for t. So I would divide both sides by 800. The 800s cancel from the right. On the left, this reduces to 12 over 8. Can reduce a little bit more. So 4 goes into 12 3 times, 4 goes into 8 2 times. I can then take the natural log of both sides. Once I've done the natural log, I can use the power rule to bring that power in front of the log. That gives me natural log 3 over 2 equals 0.04 t. Natural log e. Natural log e is 1. So we have 0.04 t equals natural log 3 over 2. And I can divide both sides by 0.04 to get t equals natural log 3/2 over 0.04. So I'll type that in my calculator to get a decimal value. That's natural log 3 over 2 divided by 0.04. And now I have 10.13, let's round to 7 there. So the insect population will grow to 1,200 after 10.137 days. There's another way to get that. We can use the intersect feature in the calculator. That's also in the calc menu. So I would go to second, calc. Oh, I need to do something first. Give me just a second. So in the y equals menu, I need to type in that 1,200 that we were trying to go to. So there's the 1,200, and on the graph, that intersection point is the number of, that's going to give us the number of days. So now I go into that calc menu. I'm going to select number 5 for intersect. It asks me first curve, I hit enter, second curve, I hit enter, and then it says to guess. You want to move your cursor closer to that intersection point. And you can see our x is getting closer to that value of 10 there. And we get the same 10.137 from our calculator. I believe there's one more part, so let's take a look at that. When will the insect population double? So we're still looking for time on this part. So we know we started off with an initial population of insects of 800. Double that 800 would get me to 1,600. So that's what I need to substitute into my equation. 1,600 for the P of t, population after time, equals 800 e to the 0.04 t. I'm going to solve this just like I solved the other one that we just did. I would divide both sides by 800. 1600 over 800 is 2. The 800s cancel on the right, giving me e to the 0.04t. Then I would take the natural log of both sides to solve that exponential equation. I would use the power rule to bring that 0.04t out of the exponent. Natural log of e is 1, leaving me with 0.04t equals natural log 2, and then I would divide both sides by 0.04. T equals natural log of 2 over 0.04. And then I'll type this in my calculator. So natural log 2 over 0.04 would give me 17.329 if I round. So it would take 17.329 days for the insect population to double from 800 to 1600. We could also get this in our calculators, making that value 1600. And if you look at this picture, you can see that I don't see the intersection point. So I'll have to adjust my window a little bit more. So let's change it to 20. And now you can see that intersection point. So I hit second and trace to go into the calc menu, select number 5, hit enter for the first curve, hit enter for the second curve, and I want to guess, move your cursor closer to that intersection point to guess. If you only have one intersection point, you can actually skip this step, but if your graphs have more than one intersection point, you need to move close to that intersection point. So you can see here we got 17.329, just like we did by calculating it by hand. Thank you for checking out my videos. Have a great day.